Okay, let's get started. And good afternoon, everyone. Today we're going to talk about some p-adic integers and Galois representations. I think like Garen and I were basically giving a lot of talks about Galois representation, elliptic curves, and maybe we need to probably refresh our refresh our learning and give a slightly different like how should I put it, perspective, talking about some more like a tangible methodology to study the Galois representation. Because whenever we say, hey, Galois representation can tell you everything, and then we never told you about, well, what is Galois representation? How do you calculate it? Why do they matter? Why is this the good tool? We didn't really talk about it. I actually asked Nara about if we have some particular topic that we better just like lay a foundation about, and she came up with this one. I think it's a very good suggestion because when I was a graduate student, and whenever I attend the number theory courses, all the professors are saying, "Oh, it's just a p-adic analysis," and they never really spend their time to talk about some details about how they are defined, what they matter, and like why they matters and stuff like that. They just say, "Oh, you can just do your own research," but it's something trivial, and yes, you need to do some studies on your own. But unfortunately, all the p-adic analysis textbook is either so much complicated or just very thick, very huge. So I just wanted to some compile my knowledge. So it's very much like how should I put it, number theoretic orientation. So maybe this is not enough to tell you the general motivation or ideas or application about the p-adic stuff, but at least this is the much of the stuff that I understand, and still it is good enough to do some research out of that. So yes, if you'd like to study or dig in more, you can check some other textbook or resources. But I think as long as you know this much stuff, hopefully this will not be too much of a hassle for you to follow our future talks, I guess. Okay, let's start with some very simplest stuff, which is the absolute value. So basically, absolute value is well, we all learned when we were in like a middle school or something, like absolute value of x is either x or negative x, depending on the sign of x. But a little bit more like, how should I put it, motivation or like an idea about the absolute value is to follow the following criteria. So it should be non-negative. Any x, the absolute value of x should be non-negative. And it should respect the multiplicativity. So xy absolute value is just a product of the absolute value of each of them. The third one is particularly important, called the triangle inequality, and we all understand what it means by. Like, if we're just getting from one point to the other point, if you make a detour to some other point, then of course that should be a longer journey compared to just a direct journey from x to y, or technically x to negative y in this case, though. And finally, absolute value of x is zero if and only if x is zero. For any other choice of x, you should never get zero. Of course, there are two very trivial absolute value one can consider. One is just too trivial, so we never really talked about it in much details. That is, it is giving zero for every zero for x, and one for anything else. Still, it satisfies all these axioms, so it's an absolute value. Another absolute value is called the real absolute value, which is, yes, what we know. And here's another type of absolute value that I like. Oh, before I talk about the another type of absolute value, we can also talk about the equivalence clauses or equivalence relation of the absolute value. So consider this just a regular absolute value, but taking the lambda power, where lambda is a part of real numbers. And you'll soon see this also satisfy the axioms of the absolute value. So taking absolute value of x as x itself or square root of x, if it isn't negative, then square root of negative x, still satisfy all these criteria. And that's also an absolute value, but we don't really want to call it as a new, very intrinsically new type of absolute value. It's just the same absolute value, but with a little bit of different like factor. And yes, so we call they are equivalent. Two absolute values are equivalent if there are some positive real numbers lambda, where one is the power of the other by lambda. And in that case, we say they're equivalents, and they basically generate the same topology. And one question we can consider is, how can we classify all the absolute values on Q up to equivalence? And here's another type of absolute value that I'd like to introduce today. So fix a prime number p. P can be any prime, 2, 3, 5. Just choose your favorite prime numbers. And we're going to call VPX. Actually, VPN, my bad. So for any integer n, VPN is h. If p to the power of h divides n, but p to the power of h plus 1 does not divide n. In this case, we call p to the h exactly divides n. If you just take a higher power, it never divides it. So for example, what is v to 24? That is, what is the largest power of 2 that divides 24? Of course, 8 divides 24, but 16 doesn't divide 24. So 8 is 2 to the power of 3, so we call this one as a 2-adic valuation. 2-adic valuation of 24 as 3. What is the 5-adic valuation of 4? 0, because 5 can never divide 4. Only 5 to the power of 0, which is 1, divide 4, and any higher power cannot do so. For 0, we just define it to be positive infinity. Just naively thinking 7 divides 0, 49 divides 0, any power of 7 divides 0, because 0 can be written as 7 to the n power times 0. So any p-adic valuation, we just define the 0 as a positive infinity by convention. So now you choose your favorite rational number, a over b, in the simplest form. So we don't want to have something like 2 over 4 because that's not going to give you a very good valuation. Let's just simplify as much as you can. And we define the p-adic valuation of x to be the p-adic valuation of the numerator minus the p-adic valuation of the denominator, which is, yes, I mean, if x is an integer, it should follow this rule because x is an integer means b is 1. And p-adic valuation 1 should be always 0. So it just matches up what we just defined up above, but now extending to all rational numbers. And we define the p-adic absolute value of x to be p to the power of negative the p-adic valuation of x. One can actually confirm that this also satisfies all the classification, all the axioms of the absolute valuation. And here's a very nice theorem that I wanted to emphasize called the Ostrovsky's theorem. Let this be any non-trivial absolute value of q. Then this is either equivalent to just a typical absolute value that are used to it, or p-adic valuation, p-adic absolute value. So intrinsically, there are only 2 types of absolute value, just a typical absolute value or p-adic absolute, yes, just typical absolute value or p-adic absolute value, and there's nothing more than that. And let's quickly talk about the construction of ZP. Like, we've been using ZP several times, but we never talked about how ZP is really defined at all. So fix a prime P and consider a system. I just called this system. I'm going to soon mention what system is. System of this one. So that basically means you just bring z mod p to the power of nz for every n. Z mod pz, z mod p squared z, z mod p cubed z, just bring everything. But they're not just independent objects, but we can consider the maps in between them. So pi ij is just a regular projection. Whenever j is larger than I, we can consider the regular projection for z mod p to the jz to z mod p to the iz. Like, for example, we can consider a map from z mod 4z to z mod 2z by reduction mod 2, z mod 8z to z mod 4z by reduction mod 4, and anything like that. And now this z mod p to the nz is not just like a collection of individual stuff, but they're all connected like a complex or cycles or like some kind of long chain with this pi map, regular projection map. And this system where we have z mod p1z, z mod p2z, z mod p3z, and keep going infinitely, and we have all the maps from the higher power into the lower power, so that this z mod pz is the like a terminal object, very last part of this whole chain, where z mod p to the infinity z is like the very initial object. This kind of thing is called the inverse system. And this kind of inverse system is studied in homological algebra. So if you have never read it, Attia and McDonald's textbook is always a good source to study the homological algebra. And that inverse limit, which is defined as follows, is called ZP, or p-adic integers. We take the z mod p and z with infinite limit, or it can be understood as a collection of xi, where each xi is an element of z mod p to the iz, but they also respect this pi map as well. So for example, if I take z2, any element in the z2 should be an infinite tuple. But each element, it cannot be a random number, but they need to respect this pi map. So for example, if my first element in the z2 is 1, then the second element cannot be 0 or 2 because 0 or 2 mod 2 is 0, not 1. So it should be 1 or 3. So it's like a branching out. If my first element is 1, the second entry should be a 1 or a 3, but nothing else. If my second entry is also 1, then the third entry, it gives me more choices, but also 1 and 5, because in Zmod 8Z, there are only 2 elements that are congruent to 1 mod 4, 1 and 5, and stuff like that. So you can imagine this one as like infinitely ramifying branches, but we are making a choice for each of them, each of the entries, so that they are somehow compatible for each finite level. Okay, moving on. Then how can we, yes, so I just mentioned that ZP, any element in the ZP can be expressed like this infinite tuples. Infinite tuple method is somehow like, how should I put it, intuitive way of understanding it. Because yes, I just choose first element, second element, third element, but they need to be like respecting their projection. But like if you're just making up a random element in this form, then you need to be careful. Is my x2 congruent to x1 mod p? Is my x3 congruent to x2 mod p? And stuff like that. It's just not really a hard job, but it's a little bit like too many details to take account. So some people just write it down as an infinite series. So how's this infinite series defined? First element A1, the first coefficient A1 is simply x1. The second coefficient A2 is defined so that A0 is x1, my bad, because we start with this mod p0. And then A1 is such that A1p plus A0, that should be equals to x2 and stuff like that. So yes, I mean, like my explanation is a little bit sloppy, but I'm basically telling you that any kind of this infinite tuple that respect to this regular projection map can be uniquely expressed as an infinite series. And we're not using the typical argument like, hey, if you're adding all the p's to the power, don't we get infinity? Yes, in the regular setting of the analysis, but in the p-adic analysis, no, we are just treating them as some finite like an element. So they're behaving slightly different in this world. Okay, so yes, we can write it down, any infinite tuple as an infinite series. And here's one quick observation. Z is contained in ZP. This map is injective. How? Just pick your favorite integer and make it an infinite tuple as x mod p squared, x mod p cubed, and keep going. So for example, 5 in Z3, 5 mod 3 is 2, 5 mod 9 is 5, 5 mod 27 is 5. Just after that, like my p power is always greater than 5, so it's going to be just infinite length of 5. So 2, 5, 5, 5, 5, 5, and keep going. Yes, I think this is quite an easy way to understand that this is 5, but we can write it down as an infinite series. First coefficient is 2, second coefficient is 1, and all the later coefficients are 0. Then you can see the first entry here should be 2. The second entry should be 5, so that 2 plus 1 times 3 is 5. Third entry, just keep 5 because I have 0 here. So 2 plus 3 is still 5 and keep going. So you can see how we liken changing infinite tuple notation and infinite series notation, vice versa with this specific example. Then you can see like what's basically happening here. So yes, you can see this kind of map is injective. It's not really hard to prove that this is injective and well-defined. So Z is contained in ZP. When I first studied about the ZP, I just felt like it's just a p-adic expression, or like we are using mod 10 expression. And is it just a p-adic, just replacing 10 by p? So I just thought Z is intrinsically just nothing more than ZP, or ZP and Z are the same thing. Well, actually, no. ZP is actually larger than Z. So think about this element and the Z3. So my first coefficient 2, second coefficient, third, fourth, everything is 1 after it, which is diverging in our usual setting when we just take our usual, like an topology, like an R infinity, like a real topology, then this one just diverges to positive infinity. However, in the p-adic number, we have different topology, and this one doesn't diverge. It actually gives you a certain number in ZP. So think about this x. And now let's imagine 2x. I'm just multiplying 2 and just using the regular number theory and regular like an arithmetic. So multiplying the first coefficient by 2, second coefficient by 2, third 2, and keep going. Because I have 4 times 3 to the power 0 for the first one, that's 4, which is 1 plus 3. So make the first one as 1 and bring this 3 to the next level, like when we are doing just a regular addition and the base 10 calculation. But because I have 2 times 3 to the power 1 already, once you get this extra 3, then that's going to be 3 times 3 to the power 1, which is pushing it. Like I get 0 times 3 to the power 1, but pushing it to 2 times 1 times 3 to the power 2, which contributes to this 2 times 3 to the power 2 again, push it forward, and everything behind, like the dominoes, they all just flip over, get 0, 0, 0, 0 indefinitely. So in the end, I have 1 for the first entry. Everything else is 0. That is 1. So that means x is some valid element in Z3, and 2x gives you 1. So we can interpret this one as Z3 has 1 over 2, or more accurately, ZP has an element x that gives 2x is equals to 1. So ZP is now larger than simply Z, because Z doesn't have 1/2, but ZP has 1/2 in the case of P is equal to 3. And actually, one can prove it using some number theory. A and B be co-prime integers, and P doesn't divide A, then there is some element in X in ZP such that AX is equals to B. Or another way to understand this, like there's something like B over A and the ZP. So it just contains some rational numbers, so it should be larger than Z. However, a quick spoiler, the Z3 doesn't have 1 over 3. It has 1 over 2 because the denominator 2 is co-prime to 3, but the denominator is not co-prime to P, your choice of P, then it fails to have that element. So it's not exactly Q, but contains quite many elements in Q, so we see that CP should be larger than Z, but it cannot be just identified as Q because it will lose some family of elements, which has denominator P and divisible by P. And here are some properties of CP. I'm just using algebraic terms, and if there's any algebraic terms you are not familiar with, just feel free to interrupt me. CP is integral domain. Yes, integral domain. I think I've read this terminology like 5 years ago and totally forgot about the existence of this terminology. But it means x times y is 0 in ZP, then x is 0 or y is 0. So it behaves like an integer, but it's a domain. ZP has a unit. So any element in ZP that is a unit is in the form that A1 is non-zero. So, I mean, not A0, but should be A0, my bad. The first coefficient should be non-zero, or if you write it down as an infinite tuple, the first term should be non-zero. It's a local PID. First of all, local means every prime ideal is maximal ideal. PID means every ideal is principally generated. Principal was it? Like generated by a single element. So yes, any ideal in ZP is of the form like this one. And we get the maximal ideal only if k is equals to 1. And yes, I mentioned ZP is not a field. P is in ZP. If I write it down P as an infinite series, it should be 0 for the first one, 1 for the next one, and everything else should be 0. But 1 over P, as I mentioned earlier, we don't have that element in ZP, so it's not a field. ZP is uncountable because if you write ZP as an infinite series, then A1, A0, A1, A2, A3, it can be just any element, any numbers in between 0 and p minus 1. So the ZP is equinumerous to the like some finite set to the power of infinity, which is uncountable set. And finally, ZP is actually, this one is QP, my bad. Sorry, forget about complete. ZP is a metric space with a distance function like this. Sorry, this is a typo. I meant QP is a complete metric space, but yes, ZP is a metric space where this distance is defined to be distance between x and y as p-adic absolute value of x minus y. So in this world, oh yes.
Oh, I have a quick question. On the second point, shouldn't it be A0 as a unit?
This is A0. I made another typo here. Yep, thanks for pointing out.
Oh, okay.
And say the definition of the third point. What is a local PID?
Local PID. Local means every prime ideal is a maximal ideal. So one example of the local.
I don't know about that. I think local means local ring.
Yes. Sorry. What is your last question? So you said.
Do you mean local ring?
Local ring. PID is a principal ideal domain. Principal ideal domain is every ideal is generated by a single element. So like a Z is a principal ideal domain. What is ideal in Z? Just any integer times Z. Like 2Z, 4Z, 6Z, these are all the ideals. We can generate an ideal with 2 elements, but you can uniquely you can write it down as a 1 element generated ideal, right? So if I think about what is the ideal generated by 2 and 4, that's basically the same thing as ideal generated by 2. There are some rings that cannot be, that has some rings, they have ideal that are generated by 2 elements, but you cannot generate it with a single element. In this case, this is not a PID. Principle is not the case.
I think Garen's question would be the following. So the local PID just means the local ring, which is also PID. I think that's the...
Yes. Yeah. Local PID is a local, so every prime ideal is maximal, except for the 0 ideal, of course, and it also needs to be principal ideal integral domain. So every ideal is generated by a single element. And
local ring is it has a single maximal ideal, right?
Doesn't really need to have a single.
Yes, localization makes the local ring, which makes the only maximal ideal. That's the meaning.
Okay, maybe I got confused.
If my undergrad curriculum, if I still remember my undergrad curriculum, ZP has a single maximal ideal, which is P times ZP, I think. Please tell me if I'm wrong. Yeah, okay.
You're right.
Okay, that's my question. Does ZP have a single maximal ideal, the ideal P times ZP?
Right. Sorry, actually, you're right. I'm just reading the Wikipedia page. I got confused. It's not that every prime ideal is a maximal ideal. That's the case. That's the Dedekind domain, if I remember correctly. Yes, I learned quite a long time ago, so it's also confusing. But yes, local means we only have a single maximal ideal. You're right, like that. So we have only a single maximal ideal, which is TZP, case 1. And every ideal can be generated in this form, so single element, p to the power of something.
I think ZP is also a Dedekind domain.
Yes, I think ZP is a Dedekind domain. So in the end, in this setting, everything will be the same. But in general, Dedekind and the local PID are different. Local PID is sometimes called as a discrete valuation ring, GVR as well. Yeah. And yes, it seems like I have some typos here, so I'll just correct it later, and then in the version that I'm going to upload, I'll just correct everything just to make sure. Yep, thanks for pointing out. Keep going. And I think this is a very good diagram to tell you like how the element, what is like the distance relationship between the element and the ZPs. Of course, this is not a complete diagram because it doesn't contain something like rational number. It only contains the integers numbers here. But in this world, two numbers are close if they are both divisible by p to the high power. So like 0 and 9 are relatively close because 3 to the power of 2, which is relatively higher power, divides both 0 and 9. 0 and 2 are totally in the opposite, like the side of the globe, because 0 to the power of 0 divides 0 and 2, right? If you have two co-prime numbers, then of course there's no any powers of 3 that's going to divide both of them, so they're just very far away. So yes, in our like an intuitive way, we understand z as like some parts of the number line. They're all like apart from each other, starting from 0, 1, 2, 3, 4, and -1, -2 in the other side, and we can define all the distance in that way. But now this ZP is basically reshuffling of everything into a very weird way, so that whenever p to the very high power are dividing both of the number, in our regular setting of the number line, they should be a very large number, so they should be very far apart. But in this p-adic, they should be very close now. So we are reshuffling everything to redefine the metrics and the distance. So I think this is a very like a useful diagram to understand how the ZP behaves. And yes, what is the QP? QP is the field of fraction. Yes, as we mentioned a little bit ago, ZP is not a fraction, not a field, because P is there, but whatever P is not there. But we can define QP so that it's closed under multiplication and division by making it the field of fraction. How do we do it? We just put 1 over P squared, 1 over P cubed, and everything like that, and just take an infinite union like in this way. So now what does 1 over P represent in here? Again, I can write it down as an infinite series, and we can all expect that 1 over P in this element should be 1 times 1 over P, and all the rest of the terms should be 0. So that if I multiply P to this one, it'll be 1 times P, 0 times P to the 1, 0 times P to the 2, and it'll be 1. So now it has an inverse of P, so QP is a field. Okay, so I think I've given some like an enough idea of all these p-adic integers, QP, and stuff like that. We're gonna see some now we're gonna see some application of the p-adic numbers and stuff. One of the most useful application, I think, is a p-adic character. So let zeta pn be the p-nth root of unity. Then every root of x to the power of p to the n minus 1 is of the form of zeta p to the pn to the power of some k. I said k coprime to p. Actually, this is not true. I mean, I just made another typo here. The primitive root, yes, but maybe not for the general cases. Yes, I wrote down this one quite a long time ago. So yes, I think this is another typo. Just here, yeah, if I just restrict my attention to the primitive root, then yes, but otherwise, I think any power should still satisfy this equation. I need to double check this one, sorry. So because every root of this equation is of the form p to the n, zeta p to the n to the power of k, I can consider this Q adjoint zeta pn, which should contain every root of this one. So it's going to be the splitting field of this one. And any automorphism, this field, we'll be sending zeta to the sum power of zeta. And now the k should be the coprime to p. In that case, the automorphism, because you need to shuffle, but you cannot map two different roots to the same root. So it should be some k coprime to p, and that's going to permute the roots of x to the power of pn minus 1. So we can consider a map where chi-n take a sigma in this one, because this sigma, the Galois automorphism, will be shuffling all the pnth root of unity. It can be understood by taking, okay, so take a sigma, where the sigma takes zeta pn to, zeta pn to the power of k, and stuff like that, and we can just map it inside z mod p to the power of n. Technically, this is, I just put an injection, because to make it a surjective, it needs to be the group of root of unity. So I need to take x there. But in general, I'm just going to talk about this one as an injective function into this a little bit larger set, where we define sigma zeta pn. It will be some zeta pn to the power of k, and I'm going to define that k to be this chi n of sigma. Now let mu pn be the pnth root of unity. So mu pn is isomorphic to z mod pnz, because now only zeta pn or any power, now only zeta pn or any k to power k coprime to p is there, but any basically k power should be there, so it should be z mod pnz as a z module. Also, we can consider an inverse system. As I mentioned in the earlier case, we can consider the inverse system using z mod pz, z mod p squared z, z mod p cube z. We can do the same kind of construction with mu pn, pnth root of unity, mu p squared, mu p cubed, and keep going, where this map is sending z to the zeta to the power of p. If z is some p cubed root of unity, so if you take the p cubed power to z, then we get 1. Then z to the p will be p squared root of unity. So that if you take a p squared power here, it'll be 1. So it behaves like this. So this map is slightly different, but still we can consider the inverse system using this kind of construction. Then what happens? First of all, let R be the restriction map. So here, this is the absolute Galois group. It just contains all the Q bar, all these like algebraic closure of Q, because Q zeta Pn is of course a subfield of Q bar. We can consider this restriction because this is basically all the sigma that respect Q, but can shuffle everything in the Q bar. But we can just restrict these sigma to the Q zeta to the power of P. Yes, now it's going to shuffle everything to the Q zeta P while fixing Q. And that's going to give all the map to each finite level, R1, R2, R3. And yes, I talked about there is some injective system, inverse system, mainly because of this one. Mu p squared, mu p cubed has an inverse system. And we can basically make the inverse system on the Galois Q zeta Pn in a similar fashion. And for each level, we have a chi1, chi2, chi3, which is the map we defined at the previous slide. And we can take the inverse limit to the chi's. So we define chi without any subscript as a map. What really happens here is from Galois Q bar to Q, we make restriction map to Galois Q z p to the infinity over Q, which goes to z mod p to the power infinity z, which is actually the inverse limit. So it should be z mod p z cross. And this can be understood as just 1-by-1 matrix. Any ring can be just understood as any element in the ring can be just understood as a 1-by-1 matrix. And because it's invertible, it's GL1. And it's invertible means it should have unit, it should be invertible, it should have an inverse element. So that's basically interpreting everything as a matrix. It should be a general linear group with 1-by-1 matrix, so GL1ZP. Where chi sigma is defined in this way, and that's how we define the p-adic character. And yes, just to let you know, this chi sigma should be an element in ZP cross, and I told you ZP, any element in ZP can be understood as an infinite expansion or like an infinite series. Here for infinite tuples, here I'm just interpreting this one as an infinite tuple. Well, this is the first element, chi1 of R1, which is an element in Z mod PZ cross. What's the second element? Chi2 of R2, which is an element in here, but it should be respecting to the first element with mod P and keep going as an infinite tuple. And that's basically the definition of p-adic Galois representation. So it's a continuous homomorphism. I'm going to skip quite many of this topology term, but anyway, it's a continuous homomorphism from Galois Q bar over Q. So we just take all the algebraic closure over Q. So this just pick any Galois automorphism respecting Q, but it can shuffle any root of whatever the polynomials, but map into GLDQ Yeah, in general, we just call it as a QP, but in p-adic character case, it's very specific that D was 1 and Q instead of using QP, we were using CP there. So about continuous means every preimage of an open subset should be open subset. That somehow underlying the idea that this one, each of set, you can define the topology. Yes, you can define the topology, and you can talk about the open set and closed set, which is quite an interesting topic, but I don't want to delve into too much details about that one. So yes, you can just think of it as, oh, you can define a topology in each of that, and we want them to be continuous. So chi is a p-adic Galois representation with D is 1, not necessarily need to sit in QP, but simply in ZP. So my next question is, okay, so this p-adic character is working on mu pn, which is the root of x to the power pn minus 1. But that's just a one variable equation, or like a one, how should I put it, maybe a one-dimensional stuff. How can we make it something like a two-dimensional stuff? Because GL1QP or GL1ZP can be understood as some one-dimensional object, and you're thinking about all the invertible map there. Well, what about two-dimensional stuffs? And that's the natural analog to extend the scalar representation to the elliptic curves. Because elliptic curves, we've seen quite many cases already. Any like an endomorphism or any kind of shuffling there is basically some GL2 or some 2x2 matrices. So we're going to define the Galois representation on the elliptic curves as well. So the first question is, what is the analog of mu pn in the elliptic curve case? What is the inverse system that is analogous to this mu p or ZP cross in the elliptic curve case? That is, of course, p-nth root of unity, but now p-nth torsion for the elliptic curve. So p-nth torsion means take all the points in the elliptic curve, or if you just add itself p to the power of n time, it gives you O, which is the identity element we take in the elliptic curve, which is known to be isomorphic to z mod p to the nz times z mod p to the nz. And yes, if you're a geometric person, this should be a very obvious thing, because elliptic curve is basically c quotient by lambda, so it can be identified like a trapezoid, no, parallelogram with the parallel sides are identified. So it's just some two-dimensional plane or stuff like that. So find all the points on that parallelogram. If you add n times, it just gives you the origin modulo the side. Of course, just take the n number of the points along the x-axis and the slant axis. So it should be n z mod nz times z mod nz. If you have some geometric perspective, this is a very simple fact. If you just try to prove everything in number theory, it can be very hard. But then we can consider the inverse system using this one as well. P torsion, P squared torsion, P cubed torsion, and all the way up to infinity, where we are sending P a point in here to P times P. Yeah, see, there's so many P's, so maybe I should have chosen a different letter here. But yes, you can see if I add a point here, P cubed times, it should be 0. Then this point, if I add P times P squared times, they should be 0 there. So this just gives a very natural way of maps in between, and it gives you an inverse system. And now let's QEPN, like when we did for the p-adic character, D1 case, we adjoins Q adjoins all the roots of unity x to the power pn minus 1. Now we are adjoins all the pn torsion points in Q. So this field is adjoining all the coordinates. P can be written as x comma y, and just put everything there. And then we can define this field obtained by these coordinates. It's often called as a p-nth division field or a p-nth torsion point. And then we can consider a map, Galois QEPN over Q, to the automorphism of Pn, because like in the previous case, if I go back here, this any Galois automorphism they are shuffling the roots in here so it can be injected inside the Z mod P and Z. Now, here, these automorphism will be shuffling the p-n torsion point, which is composed of x and y coordinate, and that can be identified GL2 Z mod P to the n. Basically the same fashion, but a slightly different setting, because now we are dealing with the dimension 2, not dimension, but we have 2 basis case. I just got a chat from Gunny, and I just want to quickly have a look. It says, one geometric perspective remark, inverse limit and direct limit are defined as co-limit and limit in homological algebra, which are coming from abstraction of interpreting the Taylor series. Okay, I didn't know that. Taylor series, number theory abstraction towards replacing Cx to Z. Algebraic geometrically, direct limit corresponds to the collection of Taylor series at chosen points, whereas inverse limit corresponds to the collection of Taylor series at each point. As global rational function and Taylor series at each point is slightly different, this makes distinction between Q and ZP. This is not obvious, not even close in any angles, but this is indeed super beautiful. This gives an algebraic concrete way to extract discrete information from a abelian variety. I want to note that this algebraic abstraction are indeed coming from line. Okay, that's a thing that I never know. Yes, thanks for filling out. Like, you know, number theorists, typical number theorists, they usually compute, they don't really try to understand some geometric intuition or like a motivation for all these limit and co-limit. It's just, for me, I've been doing like my advisor said, oh, just take the inverse limit. Okay, but I never really questioned that. But yeah, knowing about that this is some kind of like abstraction of Taylor series is quite a very interesting remark. I'll share the concrete note regarding regarding your comments, so all of the number theorists can appreciate it together. Please. Yeah, so yeah, if you have some notes, maybe ready by later time, it doesn't need to be like by today, just take your time. I'll share it on the website, the IMPS website, please. Okay, so anyway, we can basically do the same game, but now instead of Q zeta Pn, but with QEPN. And now I'm just going to call chi, replace chi by rho EP. Now it depends on the choice of the elliptic curve, so I need to put the subscript of the E, because if I choose a different elliptic curve, of course, still this will be isomorphic to Z mod PNZ times Z mod PNZ, but some points may be already rational, so no matter which point you pick up, no matter which Galois automorphism you pick up, it will be fixed. It will be not moving at all. However, the other cases, it may be shuffled. So it all depends on the choice of elliptic curve. So now the subscript E is important, and we can consider this kind of diagram. And then taking the inverse limit, we have this, which is defined basically the same idea. First, we take L Q bar Q, restrict it to whatever defining level you want to, and then take the rho EPN, to interpret this one as element. It's a 2x2 matrices with every element and every entry is in Z mod PNZ with respecting all these levels. And yes, here are some like interesting results out of this p-adic representation of the curve. Now, unlike the p-adic character is still interesting, but it's not really various or like variant version, because there's only one way to define the p-nth root of unity and the set of filtered rational numbers. But for the elliptic curves, as I mentioned earlier, it all depends on the arithmetic like property of the elliptic curve. So maybe for certain elliptic curves, this rho EP may be surjective, or rho EP may not be surjective. Rho EP may be surjective, but not rho EP scored as surjective, or some very different things can happen. However, no matter what you choose, rho EP infinity is chi p, determinant of rho EP infinity is just chi p infinity. So yes, p-adic character. I mean, if you take the determinant on this p-adic Galois representation, then we get the p-adic character that we just defined earlier. And determinant of rho EP infinity is surjective. I think this is what Garen mentioned last time. Yes, it's really important that the determinant of the Galois representation is always surjective, and that really quite like narrow down. Whenever you want to understand the image of the Galois representation, you don't need to search for everything, but you can only focus on the groups that has a surjective full determinant group. And this is quite an important theorem. Yeah, sometimes called the value pairing steps. Another important theorem is Serres-Oppenhu's theorem. That is, if E is a non-CM elliptic curve, non-CM means it has no complex multiplication, endomorphism ring of E is just Z, just adding itself an integer number of times. If E is a non-CM elliptic curve, for any prime P, this image of rho P infinity, which is a subgroup of J to ZP, should have a finite index. Furthermore, for all the finitely many P, they're just the same groups. So p-adic Galois representation, most of the cases for all the finitely many, they're always surjective, except for very few. For these very few exceptional cases, still this image of rho P infinity should have a finite index, so it should be very large compared to this. It should be a relatively large group. It cannot be a finite group or something. I think this is a very interesting thing. If E is a non-CM elliptic curve and P is at least 5, then rho P is surjective if and only if rho P infinity is surjective. So yes, here I said all these now depend on the choice of E, and I said maybe some cases rho P is surjective but not rho P squareless. Maybe it's surjective everything. Maybe it's not surjective at a certain finite level. Like maybe it's not to rho P cubed, but starting from rho P to the power 4, it becomes surjective. It cannot be the case that everything is not surjective, because in that case, it will have infinite index. But at a certain level, it should stabilize to be surjective and keep going on. But they may be dependent on the choice of P, but a nice theorem of Serres is if P is chosen at least 5, rho P is surjective if and only if rho P infinity is surjective. So if you want to see what's happening in the p-adic Galois representation for P greater or equals to 5, you only need to check at the rho P. And here are some counterexample, what happens for 2 and 3. And yes, sounds like a very specific examples. And whenever some very famous mathematicians make this kind of like discovery and announcement, it's really easy to just take it for granted and you don't really check it on your own. And it's kind of really hard to check it unless you are able to use Magma or Sage. And by the way, I'm really bad at coding, so it's kind of hard to really check whether this is the case. So I'm going to tell you how to do it with the LMFDB. So by the way, whenever mathematician number theory is B2, I'm so bad at coding. Yes, so that's why I have, whenever I'm making up the group project, like collaborative research project, I always secure at least one coder in my group. and yes, so whenever you see some number theorist or elliptic curve talk, they always put their LMFDB label. So I'm going to tell you how to use this LMFDB database. So let me quickly pause my sharing and share another screen. LMFDB is L functions modular forms database. Here they are. So they have a lot of stuff. They have elliptic curves over 2, elliptic curves over some number field, a billion varieties of finite field, number field, p-adic. There are a lot of stuff. That's your new playground. So let's only focus on our example. First example is the LMFDB label is 1944F1. Then we can write it down here. There are several different ways to type the label. One easy way is to stick with LMFDB label. But if you know only of the coefficient, because any elliptic curve can be written as in this way, then you can also search this elliptic curve using these coefficients. So you can have a look later. But in this case, I already know the LMFDB label, so I'll just type the LMFDB label. Now we get the glossary or encyclopedia about this elliptic curve. Yes, so this is the elliptic curve that Elkis found out, where rho 3 is surjective, but rho 3 infinity is not. So here we have Weierstrass equation, model value group, its Q torsion, its rational points is isomorphic to Z. Generator, integral points, conductor. By the way, this 1944F1, this 1944 means conductor, and basically conductor is some bad primes where you cannot define the reduction mod P with some power. But it's okay if you don't understand what's really happening with the power. Just if P is 2 or 5, then you cannot reduce this one to mod 2 and 1. That's just an easy way to understand. F1, F means, because Garen already gave a talk about the isogenic class, this, whenever you see F, or maybe I think it should be somewhere here down. Okay, so if I give you some different elliptic curve quickly, so say 1944.
John, move up, go back.
Yes.
Go back to 194. You see to the right, related objects, isogeny class 1944 dot.
Isogeny. Here. This one? Yeah, so if they share the same first letter, it means they're in the same isogeny. So any elliptic curve, so in this case, it only has one elliptic curve in this isogeny, but any elliptic curve, it has a conductor number and some alphabet. This alphabet means whenever you share the same alphabet with the same conductor, they're the same isogeny class. And F1, F2, F3, that means the first element, first elliptic curve, second elliptic curve, stuff like that. I don't know how they order them, but that's how you basically understand this one. So if I click 1944, it gives a list of elliptic curves whose conductor at 1944. In this case, quite interestingly, each elliptic curve forms its own isogenic class. They are not isogenous to each other. But there are some elliptic curves with A1, A2, A3, A4 to A6. That means these 6 elliptic curves are isogenous to each other. But yes, this is 1944. And there are many interesting things you can have a look around. Here are some Burton-Swinnerton diet related stuff. And this is where you can find the adelic Galois representation at the finite level. This is also a very useful tool to understand the Galois representation, but I'm not going to talk about this one too much detail. But looking for, here it is. I think this is what I'm interested in right now. Here, a Galois representation. The L-adic Galois representation has maximal image for all prime number except for the table below. This means, except for 3, any L-adic Galois representation is surjective. So 2-adic, 5-adic, 7-adic, they're all surjective, except for 3. But it says mod 3 image, so row 3, that's a 3G, and actually 3G, this one is the full group. Yes, so mod 3 Galois representation is surjective. However, 3-adic image, this one is generated by these 2 elements, and you can see the index is not 1, but 27. Here the index is 1. Index is 1 is, of course, it's the full group, but here index is 27 means it's not a full group. So yes, 3-adic image is not surjective, but mod 3 image is surjective, and this is the example that Elkis found out. As we mentioned earlier, Sarah's theorem says that mod P is surjective, and p-adic should be surjective if P is greater or equals to 5. But there are some counterexample for 2 and 3, and this is one example where 3-adic is not surjective, even though mod 3 is surjective. Another example is proposed by Jeremy Rouse, who's in Wake Forest, and David Zurich Brown. I don't know where he is currently at right now. And they come up with an example with the 2-adic case. So their example is 162.d2. So yes, you now know that the conductor is 162. Isogenic class is D. D2 means it should have at least one elliptic curve that is isogynous to this one. D1 and D2 should be isogynous. And here, in this case, Galois representation, any prime except for 2 and 3, their p-adic Galois representation should be surjective. 2 and 3 are the only cases where the bad thing happens. For 2, mod 2 Galois representation, index is 1. That means full group. But 2-adic Galois representation image, index is 16. That is not full image. What about 3? Okay, so this is the mod 3 Galois representation image. Index is 8, so it's not 1, so it's not full. And this B stands for Borel subgroup. There's some number theorist's way of classifying all this possible Galois representation image using like a Borel subgroup, split Cartan group, normalizer split Cartan group. There's some classification of this one. But anyway, yes, this is Borel subgroup, and Borel subgroup is not the full group. And 3-adic Galois representation is still index A, so it's not full image again. So yes, I think this, if you are really into this kind of Galois representation mod P or p-adic, this LMFDB, particularly this Galois representation page, be a very useful resource that you can just basically find out everything. And yes, I think this one is LMFDB, but LMFDB, there's a beta version as well. And beta version, they just let you find a little bit more refined search. So not only about the conductor, because currently if you go to the elliptic curve here, we can only find based on the conductor, discriminant, J invariant, rank, and stuff like that, label of coefficient. But I think the beta version, they let you find based on some more information. To see a chat, John makes mention of prime-adic image almost completely proven. Yes. Thanks for sharing the papers. Yes, prime-adic cases, because 2-adic, 3-adic already studied by Rouse and Zurich Brown and Voigt and Sutherland. And as we mentioned earlier, for 5-adic, surjective if and only if mod 5 is surjective, or same thing goes up for a larger prime. So there have been quite many research on the 2 and 3-adic, and they make quite a good accomplishment. Of course, this doesn't mean that we know everything, because we only talked about the prime number cases. What about the composite number case, like mod 6? Oh, by Chinese remainder theorem, is it just simply mod 2 times mod 3? Not necessarily. Some weird thing happens, and that weird thing is called the entanglement. There has been some study and the research about this entanglement, basically on, I think, Lozano Robledo. I mean, the Albert is also working on that one. Melrose is working on that one. And Harris Daniels, if I remember correctly, they're working on that one. I actually met Melrose at the JMM this year. I just told him, like, oh, actually, we are reading your paper to do our research, and he was so much happy with it. And yes, he was such a nice guy. And yes, Garen is correct. That program, that kind of classification of p-adic or m-adic Galois representation, is called the Majors program. It's a very ambitious program, I suppose. And yes, there has been quite a huge progress recently, thanks to Sutherland and all his crews doing some concrete calculations using Magma, Sage, and stuff. Okay, so this is how you play around with the LMFDB, and now let's go back to the slide. Yes, so I think I better giddy up, Perry. So yes, this is basically what we just verified. I think this is one last thing that I want to point out. So I'll just go over relatively quickly. So just pick any isogeny. Isogeny is a surjective map with a finite kernel that respect the how should I put it, the group structure of the elliptic curve, because you can define the group structure in the elliptic curves with all the identity elements and just adding the point. And isogeny is somehow respecting that one. It needs to send the identity to the identity. And the degree of phi, we just defined it to be the size of the kernel, because it said the finite kernel should be a finite number. So if you define the isogeny between an elliptic curve to itself, of course you can define isogeny between two elliptic curves, but now I'm only focusing on the elliptic curve to itself, like an endomorphism. And phi respects the group structure, so we can restrict our attention to the p and torsion point, not just at any point in the elliptic curve, but the p and torsion point. And that's going to induce a map as well. And we take the inverse limit. As I mentioned, yes, we can take the inverse limit because it will form the inverse system. We define it as a Haight module. p-adic Tate module, TPE, and that's going to induce the map on the Tate module, which I'm going to write down as VP. Then Tate module, because at each finite level, EP and the Z mod P and Z times Z mod P and Z, the Tate module that can be identified as Z mod P times Z mod, not Z mod P, p-adic Z times p-adic Z. Just set V1 and V2 to be the p-adic basis. Then this PPV1, the first basis, it can be sent to some basis, AB1 plus BB2. For V2, it can be just sent to some addition of some combination to V1 and V2 as well for some ABCD. So we can write this VP as a 2x2 matrix. Yes, determinant of VP is equals to the degree of V, and trace of VP is 1 plus degree of V minus degree of 1 minus V, and that's quite an important theorem. That is, this VP, it seems like we just chose P anything, but it actually doesn't depend on the choice of P. It only depends on the isogeny that you picked up in the first place. Yes, in particular, the determinant and the trace of VP do not depend on the choice of P. Why does it matter? Because it really gives us a very nice corollary that I use all the time whenever I'm doing the mod P reduction of elliptic curves. So just choose two distinct primes, sigma be the Frobenius endomorphism for EFQ bar to the EFQ bar. So Frobenius endomorphism basically means sending x comma y to x to the q, comma y to the q. And you see sigma p is equals to p, so x to the power of q is equals to x, y to the power of q is equals to y. That means x and y should be the element of FQ. So this is true if and only p is an EFQ. So now that the sigma p be the induced map on the Tate module, then by the previous slide, this trace of sigma p is 1 plus degree sigma minus 1 minus degree of 1 minus sigma. And this trace is called the Frobenius trace. I told you this one does not depend on the choice of p, but it may depend on the choice of q. So I will write it down as AQE. Degree sigma, we already, it is known that the degree sigma is q, but what is degree of 1 minus sigma? It is size of the kernel of the 1 minus sigma, but kernel p is in 1 minus, p is in the kernel of 1 minus sigma means p should be equals to sigma p, because kernel means it should be the 1 minus sigma of p should be 0. That means 1p is equal to sigma p, that is p is sigma p. And I mentioned earlier, sigma p is p if and only p is at q point. So this degree actually gives you the size of the EFQ. So just reinterpreting this one in this way, we get the number of the points in the FQ reduction is equals to degree, which is q plus 1 minus Frobenius trace. So, and as I mentioned earlier, AQE does not depend on the choice of. And this one just basically is a very much like a foundation of any kind of studies on the size of the reduction of the elliptic curve. So whenever I'm doing the studying how the size is distributed, I just need to study Frobenius trace, because the size of that reduction only depends on the choice of q I chose and the Frobenius trace at that level. And this really helps us identify when this one has a prime size, when this one has a square free size, or any kind of interesting properties. You can define it and study their study their distribution of these properties. And yes, I think I better stop it here. And if you have any questions, just feel free to turn your mic and ask. Jackson Morrow was a graduate student of David Zurich Brown. Oh, yes, that's right. Yeah, I think I read his name in DCB's paper, and I did. Yes, he was a graduate student there. He is currently a professor at the University of North Texas, if I remember correctly. His wife is also a number theorist. So actually, this year when I attended the JMM session, which is about the algebraic and analytic aspect of the L function and the curves, that one was organized by his wife and he was there too. So it was my first time seeing him. I actually saw his wife sometime earlier, and yes, they were so nice. I generate the node for algebra bridge between the geometry and the number theory, how to interpret algebraic data today. That's great. Is it okay if I share it on my website as well?
Absolutely.
The ideas?
Yep.
Yes, I'll do so. Okay, then I'll stop recording.